So we come now to an important type of series called a geometric series. We've already seen what a geometric sequence is. A geometric sequence starts with a constant called c and a common ratio called r, and it simply has a general term defined by as cr to the n, usually starting with n equals 0, but we could start it at any place. So if that's the case, then the sum from n equals 0 to infinity of cr to the n is its corresponding series. In other words, this is a geometric series. So just for an example, let's suppose that we have a geometric series with c equals 1 and r equals 1 half, starting with 0 with n equals 0. Then the geometric series is the sum from n equals 0 to infinity of 1 half to the n. Well, 1 half to the 0 is 1, 1 half to the 1 is 1 half, 1 half squared is 1 fourth, 1 half cubed is 1 eighth, 1 half to the fourth is 1 16th. So the geometric series is simply adding up all of these terms. Now, one of the reasons the geometric series is an important series is that we understand we can understand very clearly when the series converges and when it doesn't, and also there's a very nice formula for the sum of a convergent geometric series. So what we want to do is find the sum of a geometric series using the definition of the sum of a series. In other words, we're going to do this as the limit of sequence of partial sums. So let's suppose that s is equal to the sum from n equals 0 to infinity of r to the n. In other words, I'm just going to do this in the situation where c equals 1 and r is just r. I'm not even going to write it, it's just r. It's a common ratio. And where I'm going to start with 0. So what we're going to do is we're going to write out the nth partial sum. So the nth partial sum, Sn, is going to equal 1 plus, the terms up to n. So it's going to be 1 plus r plus r squared plus dot 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 plus r to the capital N. So that's what Sn is. All right. So you might say, well, that doesn't look like it's really getting us any place. Here's what I'm going to do. I'm going to multiply this entire series by r. In other words, I'm going to multiply both the left and right side of this equation by r. So this is r times Sn is equal to, I'm now going to multiply each of these terms by r. So 1 times r is r times r is r squared times r is r cubed, and then over here I have r to the n times r is r to the n plus 1. Now why would I want to do that? So remember when you were in algebra and you learned how to solve problems that look sort of like this? X plus 2y equals 6. Maybe we have x minus 2y equals 11, and you learn that you can simply add two equations together, giving us 2x, then 2y, and negative 2y comes out to 0, and so that becomes 17, and you can solve the equations that way. This was called a system of equations. So using that technique, what I can do is I can add these two equations together using this very long equal sign, or actually more precisely, I'm going to subtract one from the other. So if I have Sn, or one copy of Sn, and I subtract r times Sn, what I get is 1 minus r times Sn on the left. And now here, what I'm going to get are a bunch of cancellations. Looks like I have 1 and nothing matches that, so I have 1. And then I've got r minus r, so these are going to cancel. If you're wondering why I'm canceling two positive r's, remember I'm subtracting the bottom equation from the top. So then I have r squared minus r, that's nothing. There's an r cubed here, you don't see it, but that's nothing. There's an rn term. It's right where I'm pointing here, so that's going to cancel. Again, you don't see the rn on the bottom, but it's there. So what I'm left with is simply this 1 that I've already put down there, and I'm subtracting out r to the n plus 1. Again, note that even though I'm saying plus r to the n plus 1, I'm subtracting the entire bottom equation from the top, so this is going to become 1 minus r to the n plus 1. So what that means is that using this algebra, I have Sn, I'm going to divide both sides by 1 minus r, is 1 minus r to the n plus 1 over 1 minus r. So now the question is, when does this expression, because I'm going to have to take its limit, in other words, what we can write here is that the sum from n equals 0 to infinity of Rn is equal to the limit as n approaches infinity of Sn, which is 1 minus r to the n plus 1 over 1 minus r. So, so this is going to converge provided that this term r is between -1 and 1. It sort of makes sense because if you think about it, if it's, let's suppose it's 7/6 raised to the infinity, that's going to equal infinity. But on the other hand, if it's 6/7 being raised to the infinity, if I multiply that by itself an infinite number of times, I just get 0. So the question is this fraction, is r a fraction that's greater than or less than 1? And of course, if it is 1, then if it is 1, then the problem is that then I have division by 0, and obviously that's undefined. And if it's -1, I don't have division by 0, but what I do have is oscillation. In other words, if I take 1 minus -1 to the n plus 1, I'm going to keep either adding or subtracting 1 from 1, and which means it's just going to oscillate between 2 and 0. So that doesn't approach a limit. So the point is that this limit exists as long as the absolute value of r is less than 1. In other words, as long as r is between -1 and 1, exclusive of its endpoints. So that is okay. So if r is between 1 and -1, then that means, of course, that this term here approaches 0. Or I should do it up here. That means that this is approaching 0. In which case, what we get is that the sum from an n equals 0 to of r n equals 0 to infinity of Rn is equal to 1 over 1 minus r. And again, if the absolute value of r is less than 1, diverges otherwise. So, okay. So that's the formula for the sum of a geometric series. Let's just wrap that up. The sum from n equals 0 to infinity of r to the n is equal to 1 over 1 minus r if absolute r is less than 1. And we can generalize this also in a formula that you're going to be allowed to use. You could derive it in exactly the same way. We can say that if n equals, I'm going to start with m, because I can start this at an arbitrary place. N equals m to infinity of cr to the n is equal to cr to the m over 1 minus r. So this is a pair of formulas that gives us the sum of a geometric series. And by the way, this is also true if r is less than 1. That gives us the sum of the simple geometric series where it's just n equals 0 to infinity of just the common ratio raised to n, or if we extend it a little bit where we can start with any number m and where the series is cr to the n for an arbitrary constant c.